Hello, all. Thank you very much for giving me the chance to speak at this international workshop. My name is Prannoy Suraneni. I'm an assistant professor at the University of Miami. And today I'll be talking about supplementary cementitious materials reactivity and how to go from model systems to concrete durability. I'm really sorry that I cannot be there in person. It would have been really nice to be at IITM, but hopefully next time. All right. So a very broad overview of supplementary cementitious materials. These are low carbon cementitious substitutes, which are critical for sustainable and durable concrete. Largely in the past, we've used materials like fly ash and slag. However, these are running out in several locations because of changing industrialization trends, which means that we have to identify novel supplementary cementitious materials. We have to characterize them, and ultimately we have to use them if we want to make sure that our concrete is sustainable and durable. The biggest push for sustainability, of course, comes because cement is responsible for about 8% of all global CO2 emissions. And by using supplementary cementitious materials, this number can be cut down greatly. So if you look at global availability of supplementary cementitious materials or materials which could be used as SCMs, you can see that fillers, tailings, limestone, calcine clays, natural pozzolans, fly ash are probably the most promising. And these are global solutions, but of course, local solutions are also important because there really are a lot of materials that are available in several millions of tons just locally, which are important for this consideration. Now, the biggest thing when using these supplementary cementitious materials is how we screen supplementary cementitious materials or measure their reactivity. I'll talk a little bit about what I mean when I say screen or reactivity. So supplementary cementitious materials, essentially, they are either pozzolanic or latent hydraulic. Pozzolanic materials, these are ones which react with calcium hydroxide and water at high pH to form CSH. On the other hand, latent hydraulic SCMs, they do not need calcium hydroxide. They react with water to form CSH, as long as they are activated, which could be through pH, through fineness, or through other chemical means. Now, for pozzolanic SCMs, fly ash is an example. For latent hydraulic SCMs, slag is an example. These are differentiated from inert fillers. So inert fillers are materials which do not react with water or with calcium hydroxide. But this name can be a little misleading because they do actually show other reactions. For example, limestone is known to react with carboaluminate phases in concrete. But the big difference is that typically when using these materials, the replacement levels are extremely different. Latent hydraulic materials can be used up to 40% replacement. Pozzolanic, typically you limit to about 25%, and inert, you typically limit to about 15%. It's also critical to differentiate these different materials because they have very, very different benefits for concrete durability. I will give an example with alkali silica reaction. So if you look at pumice, which is a very reactive material compared to limestone, at 20% pumice, if you look at expansion in the ASR test, it is about 8 to 10 times lower than the expansion that you get with limestone. Similarly, if you look at the replacement levels needed to mitigate alkali silica reaction, with silica fume, you can actually mitigate it with just about 8%. For fly ash, you need about 20%. And for slag, you need more than 35%. So for different durability issues, the way different SCMs operate is again different. But ultimately, you really want to separate out when you have novel SCMs, their reactivity and what classification they fall under. Now, the same question of how we measure or screen reactivity comes back to us. So big picture, let's take a look at what we could do. Could we simply use SCM chemistry? A very simple thought experiment will indicate that this will not work, because if you consider silica fume versus quartz, both of these have the composition of about 95% SiO2. Silica fume is incredibly reactive. Quartz is completely inert. And the reason for this is, of course, that quartz is crystalline, silica fume is amorphous. It is the amorphous phases that are typically reactive in supplementary cementitious materials, which is why only using SEM chemistry will not work. There are some trends that you can see if you plot a ternary diagram based on chemistry and reactivity, but really these are very approximate, and you want to use them with extreme caution. The ASTM C618, which is the standard for fly ash and natural pozzolans in the US, it uses the strength activity index test. The way this test is set up in ASTM C618, it simply does not work. You can use it, but it's not going to tell you anything about your material. So even inert fillers will pass this test because the age of testing is it's tested at 7 days. And at that time, you don't really see much reactivity from low reactive materials. The replacement level is too low. The test limit is also too low. I'm not going to go into details, but we wrote a paper about it, essentially showing that in a lot of conditions, you get essentially the same SAI for inert and reactive materials. There are a lot of tests historically which are based on calcium hydroxide consumption. These can be really useful for pozzolanic materials, but they are not accurate indicators of reactivity for latent hydraulic SCMs such as slag. Line strength and modified line strength. This is very interesting. Mike Thomas's group has done a lot of work on this, and bulk resistivity, where we've done a lot of work. These are two incredibly interesting test methods. They can distinguish very well between reactive SCMs and inert fillers, but they cannot exactly distinguish between pozzolanic and latent hydraulic SCMs. But at the same time, they are incredibly useful techniques. I'll talk just a little bit about bulk resistivity in the next couple of slides. So, sorry. What we have shown is that bulk resistivity can be used to differentiate SCMs and inert fillers. And the reason for this is that inert fillers, especially at later ages, reduce the bulk resistivity. On the other hand, reactive supplementary cementitious materials increase it. This can be seen, for example, in this figure here. So this is the control. All the SCMs that you have are increasing the bulk resistivity. On the other hand, the limestone is decreasing it. Now, this is especially true as you increase the replacement level, because for reactive materials, the bulk resistivity increases as the replacement level increases. For fillers, it reduces. The bulk resistivity is actually a somewhat indirect reactivity measure because it is affected by changes in pore solution, pore structure, alkali binding. Some of these are directly related to reactivity, some not so directly. So it can be a little complicated to interpret, especially if you're trying to use quantitative values, but qualitatively, it's a great screening tool, especially if you use high temperatures, high replacement levels, and later ages. The nice thing is that bulk resistivity is highly sensitive to reactivity, and bulk resistivity can at least be used as a qualitative durability measure. So there are a lot of advantages in measuring bulk resistivity and standardizing it. Now, I mentioned earlier that the ASTM C311 or C618 strength activity index was flawed. So we propose actually a very simple fix for the strength activity index, which is essentially to use a bulk resistivity index. On the same mortars that you measure strength activity, you can measure the bulk resistivity as well. So what we showed is that if you take a high replacement level, 50%, and a high curing temperature, 50 degrees, you will get some differences in strength activity between reactive and inert materials. And they're about 20% or something like that, 20 to 30%. If you look here, these are the reactive materials, these are the inert materials, the difference is about 20%. On the other hand, for the bulk resistivity, which is far more sensitive to reactivity, the differences are astounding. The inert materials have the same bulk resistivity as that of the control, while the reactive materials have a value which is about 1,000% or 3,000% that of the control. So differentiation between reactive and inert materials becomes incredibly simple if you use the bulk resistivity index. I won't talk further about bulk resistivity, but if you're interested in it, please do let me know. Now, I want to take a step back here, discuss broadly what the idea of most of these reactivity tests is. So all of them essentially function on the principle that you take some sort of a system where you have SCM, calcium hydroxide, and an alkaline solution. You let them react and you measure various parameters. Could be dissolution, could be heat release, bound water, etc., etc. All of them are measures of reactivity. You can change the system tremendously. You can add cement, you can add sand, you can change the composition, temperature, pH. It kind of doesn't matter to a certain extent. The basic principle is all the same. If an adequate amount of reaction occurs, then the material is an SCM, else it is not. And a lot of the tests that we are going to talk about or that have been discussed in literature work on this principle. And you can measure heat release, for example, or calcium hydroxide, etc. I've listed a lot of different tests here. I think many of them are extremely promising. I listed the references here. You can check them out. I'm not going to discuss all of them. I'll largely focus on just one, but the details are here if you'd like to learn more about these tests. Now, ideally, what we want from these tests is that they're able to differentiate inert, pozzolanic, and latent hydraulic SCMs. They can estimate or give some idea of strength and durability aspects. And we want them to be rapid, robust, reliable, cheap, simple. This is, of course, ideally, no one test is probably going to do all of these things. I'll spend the rest of the talk discussing one of the tests that we developed, which we think has a lot of promise. It's known as the modified R3 test. It's a variant of the original R3 test, which was developed by Professor Karen Scribner and several others. What we're doing is we're taking a 3:1 mass ratio of calcium hydroxide and SCM. The liquid to solid ratio is 0.9. The solution is a 0.5 molar potassium hydroxide solution, brings the pH up to 13.5. We run isothermal calorimetry at 50 degrees for 10 days, and then thermogravimetric analysis, we run it at 10 days. So this test is interesting because most reactivity tests measure just one parameter like heat release. Here we are measuring two things. The isothermal calorimetry is giving you the heat release, and the thermogravimetric analysis is giving you the calcium hydroxide consumption. Based on these two parameters, we are classifying the supplementary cementitious materials. So here is a plot of heat release versus calcium hydroxide consumption. And I'll talk a little bit more about the classification in the next couple of slides. Now, the differences with the R3 and the modified R3. So the R3 is done at 40, the modified R3 is done at 50. The R3 has added sulfates and carbonates. The modified R3 does not have added sulfates and carbonates. I'm not going to go into details of why the differences, etc., but I will cover the temperature aspect just a little bit. Now, we are measuring both heat release and calcium hydroxide consumption. And that's a lot of work, right? It's a lot easier if you just measure one thing. So why exactly are we doing this, and do we have to do it? I'm going to argue now that yes, we have to do it, but later on, I'll tell you, maybe not. So the reason we do measure both heat release and calcium hydroxide consumption, if you use only the calcium hydroxide consumption, you can get very similar values with a latent hydraulic material and an inert material. If you measure only the heat release, you can get very similar values with the latent hydraulic material and a pozzolanic material. But if you measure both of these parameters, there is absolutely no doubt which material is where. So to properly classify, to differentiate between the slag, the quartz, and the calcined clays, you have to measure both. This is the only way that you can actually distinguish pozzolanic and latent hydraulic behavior, which, of course, as we've mentioned, is critical for concrete durability. I'm going to go over several of the modified R3 results that we have so far. So we've studied now well over 120 supplementary cementitious materials, including a lot of alternative supplementary cementitious materials. So here's the graph. This is the classification. We can discuss more reactive versus less reactive, and we can also distinguish inert, pozzolanic, and latent hydraulic. So as we go away from the origin, the reactivity is increasing. As we go from right to left, you're moving from pozzolanic to latent hydraulic materials. Now, I have to point out that the boundaries are a little bit subjective. We basically got them from clustering of the various points. But really, is there a difference between a material that's here and a material that's here? That's debatable. We are working on improving these using algorithms, etc. But we have not yet come to that point. But essentially, it doesn't change the fact that somewhere about here is your inert limit. Everything about that is reactive. And if you have something that's on this side, then that's likely to be latent hydraulic. With the classifications that we've seen, you can really see that the slag is behaving completely differently from all the other materials in terms of its heat release versus calcium hydroxide relationship. Now, when we look at chemical composition effects, we have to be careful here because I'm talking about bulk chemistry. And I've already mentioned before that it's amorphous chemistry that's actually important. But of course, it's the amorphous oxide content can be a little bit difficult to determine. So I discussed just the bulk chemistry here, but we show that the calcium hydroxide consumption reduces as the CaO content increases. And this relationship is reasonably nice. Second, we showed that the heat release versus calcium hydroxide consumption, that graph, the same graph that you saw before, it depends very strongly on the chemical composition of the SCM. Specifically, the lowest slope is seen in materials which are high in silica. Aluminosilicates, which are relatively high in alumina, show a medium value of the slope. And the high calcium materials like slag show the highest value of the slope. So in principle, if all you're interested in is estimating or screening out different materials, then if you know the chemical composition, you can say, oh, my material is either here, here, or here. And then you can just measure one parameter, which is the heat release or the calcium hydroxide consumption. And you can use that to estimate the other one. So, if you're doing this in a research lab, of course, I would suggest that you measure both of these parameters. But if you're doing this in the industry, then you could probably just measure one and use it to estimate the other. If the objective is screening, we can achieve a reduction in experimental effort and cost by combining the chemical composition with one of these parameters to estimate the other one. Now, this is an important slide. So far, all the results that I've talked about are at 10 days. And I've talked about reactivity like it's just a point, right? I've said that this is the value for a slag or this is the value for a fly ash, but that's actually really not true. The kinetic effects are incredibly important. What I mean by that is if you take this particular graph, this is a figure where this is the class C fly ash and this is the class F fly ash. Now I'm showing the heat release as a function of time. If you take only the 10-day value, then you're going to say that, oh, the class C fly ash and the class F fly ash give very similar reactivity values. And that's correct at 10 days, but that's ignoring the entire path of how they got there. And this path is really important because if you look at early ages, the class F fly ash is a lot more reactive than the class C fly ash is a lot more reactive than the class F fly ash. In the first 3 days, the differences between these materials are very clear, but it's not so clear at later ages. And this is really interesting because this is exactly how these materials behave in concrete, only at different time frames. In concrete, when you look at class F versus class C fly ash react rapidly. They give high strength at about 7 and 28 days. The class F fly ash react slowly, but they react in a sustained manner. At 91 days, very often the differences in strength between class F and class C fly ashes are minimal. So this importance is this reactivity, is important to consider because you simply cannot say that class C and class F fly ash are the same because they are not. And most importantly, the behavior we are seeing in the reactivity test is actually reflective of the behavior in concrete. So what we did was that we fit power laws to the heat flow curves. And in most cases, we saw that the reaction is completed by 3 days. This is not all completed. It's not completed, but you get about 80-85% of the reaction done by 3 days. So in principle, we could reduce the test duration to 3 days. So here's a curve showing the 10-day heat release versus the 3-day heat release. And approximately, if you multiply the 3-day heat release by 1.2, you get the 10-day heat release. But this is not the case for class F flashes. You can see that they have a completely different relationship here. And if you're reducing the test duration to 3 days, it's certainly possible, but take a look at your curve. If your curve is looking like this, reducing to 3 days might not be a good idea. If your curve is looking like this, you're probably okay reducing the test duration. So a lot of caution is needed with class F flashes and other slowly reacting supplementary cementitious materials when you consider reaction kinetics. Now, I mentioned before that the R3 test is done at 40 degrees. As you can imagine, you may want to be even more careful at 40 degrees. What I mean by that is this. So this is a figure which is showing both R3 and modified R3 results for 5 class F flashes and 5 class C flashes. I've arranged them in increasing order of heat release from the R3 test. So what you see here is that if you compare the class F and the class C flashes, at 40 degrees, which is the R3 test, the class F flashes have far lower heat release than the class C flashes. In many cases, it's about 40-50% lower. On the other hand, if you look at the modified R3 test, there is very little difference between class C and class F flashes. You can see that all of these have very similar reactivity as opposed to these, which have significant differences. So what this means is that the modified R3 test is getting out quite a bit of the reactivity of the class F flashes. On the other hand, the R3 test, which is run at 40 degrees, is not. Now, there is a temperature effect on reactivity, and that temperature effect is relatively minor for class F flash, right? Because from 40 to, it's major for class F flash. From 40 to 50 degrees, you get a massive change in the reactivity. But it's not so important for the class C flash, where there is some effect of the temperature, but not so much. So if you're running a reactivity test at 40 degrees, it is very suitable for rapidly reacting materials. But for materials which show slow reactivity, you may want to be very careful with the test or extend it for longer durations, because the class F flashes are actually great materials. They're super important in concrete. They give you great durability, but not at 28 days. It takes a bit longer for that reactivity to manifest. And testing them at 40 degrees might not be enough, especially if the test duration is 3 or 7 days. If you test them for longer, you're probably okay. You want to distinguish between materials which have low reactivity and materials which have slow reactivity, right? Because something could be reacting very slowly, but if it's reacting in a sustained manner, that's not a bad thing. If something is reacting very less, but it's not continually increasing with time, that's not so useful. So these are, gets a little subjective, of course, here, but you really want to consider reaction kinetics very carefully, especially for materials which are slowly reacting. Now, one of the major concerns with some of these reactivity tests is they're expensive. An isothermal calorimeter and TGA together cost $100,000 US, which is a lot of money. So we asked ourselves the question of, can we get the same information essentially using a furnace, which costs about 20 times lower? And luckily for us, the answer is yes, we can actually do that. So we take the same modified R3 mixture and we put it in a furnace. We measure bound water between 100 and 350 degrees and the calcium hydroxide consumption between 350 and 500 degrees. And we find that there is actually a pretty nice correlation. The calcium hydroxide consumption measured from the furnace matches pretty nicely with the calcium hydroxide measured from the TGA. When you're reducing the test cost 20 times, you're not going to get data as nice. This is true. There is a little bit of scatter. The values are not as nice as they are when using a TGA, but it's not so bad, right? We are getting largely the same amount of information, and we can actually do similar levels of classification by plotting bound water versus calcium hydroxide from the furnace. Scrivener and others have shown that bound water and the heat release actually correlate pretty nicely. So the bound water can be used as a proxy for the heat release. And if you plot bound water versus calcium hydroxide consumption, this can be a way to rapidly classify materials. You can use it in 3 days, and you can use a cheap furnace to actually make this happen. So a 3-day cheap reactivity test is especially promising for standards and specifications. We are in the process of writing this paper, but the results have been quite nice. One of the things that we are interested in the most is looking at processing effects and how they affect the measured reactivity. One of the things that is most complex in the way it affects reactivity is fineness. So reactivity fineness relationships depend on the material itself, the amorphous content, how you're grinding the material, if you're doing any grinding, or if you're doing air classification or sieving, which method you're using. So let's talk first about air classification, or specifically in this case, sieving and size fractionated fly ashes. So what we see is that we size fractionated 3 particular fly ashes, A, C, and D. We separated out the below 20 micron fraction and the above 45 micron fraction. In A, which is a class F fly ash, there is no difference if you size classify based on the chemical composition. The calcium oxide content is very similar. On the other hand, if you take the 2 class C fly ashes, which are C and D, here is very interesting because the above 45 micron fraction, the coarse fraction, that would be a class F fly ash. On the other hand, the fine fraction, which is the below 20 microns, that becomes a class C fly ash. So there is a concentration of calcium oxide in the, not calcium oxide, but phases bearing calcium oxide, really. But calcium bearing phases are concentrated in the fine fraction. So when you talk about how the reactivity changes, you have to remember that the reactivity is changing because of fineness, but it's also changing because of compositional effects. So we actually measured the reactivity, and you have it here. So in fly ash A, you see that it changes by about almost 3 times. The finer fraction is about 3 times as reactive as the coarser fraction. In fly ash B, the difference is less than 2 times. On the other hand, in fly ash C, there is actually no difference whatsoever. There is not the size fraction and the coarse fraction, they show approximately the same reactivity. And this is really strange because you can see that the composition is changing here. So what's happening? Well, what's happening is that this is a very strange fly ash. It's an unconventional fly ash, which has a lot of surface porosity. So the fineness in this case is not controlling the reactivity, or at least not the fineness measured from laser diffraction, because the specific surface area is not having the same relationship to fineness of particle size that other materials have. Because of all the pores on the surface, the coarse fraction and the size fraction actually show very, very similar reactivity. There is also changes in the phase content in the coarse and the size fraction. So if you're talking about size fractionation, you want to be very careful because you can't just study 1 fly ash or 2 fly ashes and generalize. We actually studied like 6 fly ashes and we found 3 distinct types of behavior. We are again writing this up, but this just shows you that size fractionation leads to some really interesting but complex changes in composition, fineness, and therefore reactivity. Now, let's look at what happens when you start grinding materials. So when you grind materials, the grinding energy is really important. It's also important what material you're grinding. So this is a very busy graph, I apologize. But what we found was that first, if you take a material like limestone, it doesn't matter. You can grind it however you want. We did not see any change in the reactivity based on the grinding. The heat release versus D50 is a straight line. On the other hand, if you take highly amorphous materials, for example, pumice and ground glass, for these materials, we find a very shallow relationship between the fineness and the reactivity. These were subject to low energy grinding. I don't know what happens if you put them in high energy grinding. We haven't done that yet. But in low energy ball mill grinding, we find that as the fineness reduces, the reactivity does tail off, but it doesn't drop like this. It drops, in a very shallow manner. What's interesting, of course, is that for very coarse materials, we actually register them as inert because they fall below the reactivity threshold. They're not truly inert. It's just that they're so coarse that the reactivity is going to be very low unless you expose them for very long periods of time. On the other hand, we took very low amorphous content materials. In fact, these materials, when tested as is, would be inert, and we subjected them to high energy grinding. So this grinding was done using a disc mill. And here you see a completely different relationship. In a very small range of amorphous content, in a very small range of fineness, these materials go from inert to actually reactive. So we've activated these materials through this grinding process. But here the change is not just a change of fineness. The amorphous content is also changing. You can actually do XRD and find out which materials are getting amorphized. But the point here is that you get this different relationship for these materials, different from the relationship that you get for the high amorphous content materials and different from limestone. So you have a lot of different varying responses, which suggests the possibility of cleverly using chemical admixtures to tune these relationships, to develop some ideal relationships with some of these calcium aluminosilicate materials. Now, we've shown here that activation is possible, and we wanted to look a little bit more at activation. So what we did is we took these basalt fillers. Basalt fillers or basalt fines, at least the ones we tested, were inert. So we put them in a ball mill, which is relatively low energy at 100 RPM for 1 hour. And you see that essentially nothing happens. The heat release goes from maybe 30 to 40. Then we put them in a planetary ball mill, which is similar to a ball mill, but its operation is somewhat different. But the big difference is that the rate is 400 RPM. So there's a lot more energy that is being put into the basalt fines. At 400 RPM, you actually get activation, right? So the heat release is 250. Remember, our threshold is about at 120 or something like this. So we've clearly now passed a certain threshold and activated these materials. So it's possible to mechanochemically activate these inert materials through grinding. However, as you can see, the relationship with RPM or with the grinding is not necessarily linear. And we are trying to understand what mechanisms are happening. Similarly, we also wanted to see what would happen if you heated these up, melted them, and reformed the structure. So at 1000 degrees, if you heat it up for 3 hours and then you cool it down, in this case, they were air quenched, you don't see much. The reactivity does not increase beyond the threshold. But on the other hand, if you heat it up to 1300 degrees, hold it for 3 hours, and then you cool it down, then you actually get quite a bit of reactivity here. So what we found when we did XRD in these two materials is that at 1000 degrees, you still have a lot of crystalline phases. At 1300 degrees, you've actually melted almost everything. And when you reform it, you don't get much crystalline phases. So this is amorphous, this is crystalline, and that explains why this is reactive and this is not reactive. So these activation processes are complex because you're changing the amorphous contents, you're also changing the particle sizes, fineness, probably also changing morphology, etc. So we're still trying to understand some of the mechanisms, hotspot generation, etc., that is driving these activation processes. Now, we are interested in fundamentally understanding how some of this reactivity is occurring and trying to, let's say, get completely different types of reactivity that we've not seen before. So to do that, we have a NSF project which is looking at the dissolution reactivity of calcium aluminosilicate glasses and trying to combine experiments with kinetic Monte Carlo and other modeling approaches. So what we did as a part of this is we generated 8 different calcium aluminosilicate glasses with widely varying composition. We wanted to essentially cover this entire ternary diagram. We are not, this is just started, so these are very recent results. But basically, we see 5 different glasses here, which show very different overall reactivity, but also incredibly different kinetics, right? So the first 3 here, these are fast. The bottom 2 here, which are actually high in SiO2, Al2O3, or low in calcium, these show very slow reactivity. But these two show sustained reactivity, right? The slope, if you can look at that, is keep on going on. On the other hand, the composition, which is very low in SiO2, this increases very rapidly, but then it essentially stops. That's this composition. And the 2 compositions which have all 3, calcium, alumina, and silica, these are the most interesting because there are high amounts of all 3. These are the most interesting because not only are they fast, but they're also sustained. And ideally, this is the sort of behavior that you want, where you want your reactivity to be increasing very fast, but not to stop. You want it to keep on going along. So we're investigating more into the glass structure, how that drives reactivity, the possibility of developing some of these very unusual glass phases, blending of certain materials, etc. Now, I've talked about reactivity quite a lot, but there is always the question, okay, you measure reactivity, but does it actually link at all to concrete properties? So I can tell you that it absolutely does link to cement-based properties. However, you want to be extremely careful when making such links. So we've shown, for example, that the bulk resistivity, the compressive strength at later ages, 56 or 91, these show moderate to strong correlations with either the heat release or the calcium hydroxide consumption. We've shown a lot of other correlations as well with pace, mortars, and concretes, with strength, with calcium hydroxide consumption, with bound water, etc. Now, it's not difficult to show correlations, but the problem is it really depends on the conditions. First, you want to do this at later ages. You want to do this with adequate SCMs because otherwise filler effects dominate. And the most important thing is that it's not necessarily going to be a 1:1 correlation. Because reactivity is essentially a pretty simple thing. There are a lot of other factors that affect cement-based or concrete property development. A specific example is in this particular case, we had 3 different slags that we tested, and the most reactive slag, this was a slag that was extremely reactive. It actually does not generate strength at all, compared to these 2 slags, which were not particularly reactive, but they generated quite a bit of strength. Now, the reason for that is very simple. In this slag, we have meionite, which is a phase that reacts very rapidly, but it actually messes up cement hydration because it interferes with the sulfate demand. It interferes with the alumina-silica sulfate balance. So this slag is reactive on its own, but it does bad things to the cement hydration. So this is why you simply cannot link a reactivity test to concrete properties because, for example, we've seen materials which have phosphorus pentoxide, which, again, they're reactive, but this retards cement hydration. We've seen materials with high amounts of alkali or LOI, which are reactive, but ultimately they do somewhat reduce the cement strength in some cases. So you can make these relationships, but just don't look at a 1:1 relationship and go, oh, this is fantastic, I can always use the reactivity to predict strength. It's not as simple as that. Strength or bulk resistivity, for example, are commonly affected by other properties as well. But you can, of course, use the reactivity as a starting point or for screening. Exactly the same thing happens when you consider durability. So we've shown now several relationships between ASR, calcium oxychloride, and reactivity. But you want to be careful because there are also a lot of other factors that affect durability, which are independent of reactivity. As an example, we show here that if you take a whole bunch of different materials and you multiply their calcium hydroxide consumption by the replacement level, you get this sort of relationship, a logarithmic relationship. And you can kind of classify materials which will likely mitigate ASR, materials which are extremely unlikely to mitigate ASR, and materials where really you need further testing. So these materials, and these were largely limestones or other inert materials, these will not mitigate ASR. There's just like literally no chance. These materials, on the other hand, these are very reactive materials, pumice, fly ash, etc. These will most likely mitigate ASR. So if you have materials like these are promising, they require further study. And these materials, which were slags, they'll probably mitigate ASR, but they may not as well. It really depends on additional factors, and long-term testing of ASR is needed. So really, this is used for screening. You can say which materials are useless, which materials are likely to be useful, and which materials are interesting but need further study. So similarly, for calcium oxychloride damage, we can separate out materials into these materials which are really very unlikely to mitigate ASR because they have very low calcium hydroxide consumption and lead to very high calcium oxychloride contents in paste or concrete. Materials here which are somewhere in between, where they may be able to mitigate calcium oxychloride damage, but other factors might be more important. And highly reactive materials which will likely completely mitigate calcium oxychloride damage. So for each of these durability measures, reactivity does help, but you have to look into alkali, SO3, calcium oxide, LOI, air content, a whole bunch of other factors. Reactivity is a great starting point, but reactivity doesn't tell you everything. There's some really nice work from Mike Thomas's group. I listed the 2 papers here. You should check that out because that goes into a lot more detail than what I can on this topic. So with that, I'd like to conclude my talk. So essentially, the modified R3 test is great. It can be used to differentiate inert, pozzolanic, and latent hydraulic materials. I would suggest that you measure both heat release and calcium hydroxide consumption. But if you're smart about it, one can be used to estimate the other. You can actually cut the test duration to 3 days. You can get almost the same amount of information from a furnace. And a 3-day test could be really useful for standards and specifications. Reactivity fineness relationships and how processing affects reactivity, it's incredibly complicated, but there is the possibility of tuning it using, for example, grinding aids, which is interesting. We've shown that mechanical and thermal activation of inert materials is feasible. However, there is some non-linearity. The mechanisms are still being explored. Calcium aluminosilicate glasses can be really nice model systems, and they can offer exciting insights into reactivity of both conventional and novel SCMs. And we're exploring their reactivity, the kinetics, and how it's affected by glass structure. You can link reactivity to paste properties and to concrete durability. You can use this for screening. Just be careful when you do something like that. So with that, I'd like to conclude my talk. Thank you very much for giving me the chance again. This is my group. These are the people who are funding the research that we're doing. Please feel free to reach out to me by email if you have any questions whatsoever. Thank you very much.